This is Craig Shields, and I'm pleased to have on our Two Green Energy webinar today Steve Hellman, who's the president of EOS Energy Storage, who's going to give us a little presentation on storage and a particular approach and capability that EOS brings to the table. I'm pleased to, the whole thing of how I came across this company is something of a coincidence. I was sitting having lunch at an energy storage show, and right across from me was a gentleman who introduced himself, and 2 minutes later I was having a conversation that I really couldn't believe. If the capabilities here are true, this really is a game changer in a great number of ways, and I'm pleased to have Steve. Last time I was in New York, I went over and spoke with Steve in his office for a little bit, and I've become more and more convinced that this really is the real deal. Having said that, I want to be skeptical of this. We're going to be talking here about zinc air batteries, which of course have been trotted out, as they say, over the last couple of decades. We've been hearing about this for a long time, so I think the listening audience is going to be rightfully skeptical of this, and we want Steve to present this in a clear and compelling way. Steve, welcome to the broadcast.
Well, thank you very much, Craig. Thanks for inviting me, and I hope this turns out to be interesting for all concerned. I would even start by segueing off of the introduction that you just made, Craig, by saying that I've been the president of the company since the beginning of the year, but EOS has been working on this technology since 2004. And I also started with a very high dose of skepticism with respect to this technology. I have been in the energy industry for over 20 years, and energy storage is the golden fleece of the energy industry. It's something that we talk about right up there with cold fusion and some of the other things that we hope one day in our lifetime to be able to experience and to integrate into our business. And when this was brought to me back in 2008, actually, it was brought to me by my now colleague and the CEO of the company, Michael Oster, with whom I had had a previous business that we grew together in the energy field. And he told me what he was setting out to do, or what they were trying to do with the technology. Like I said, it had been developed already for about 4 years by Steve Amendola, who's our inventor. And I was very skeptical, but I had a slight suspension of disbelief, and sort of told Michael that if there was something that, if this could be done, it could, like you said, Craig, be a complete game changer. It has so many important implications. And so I said to him, look, if you can pull this off, give me a call, and let me know if I can help when you've gotten a little bit further down the line. And about 2 years later, sure enough, Michael gave me a call and said, we think you should come and check out what we've done. And I spent a couple months getting my hands dirty with what these guys have accomplished. And I have to agree with you, Craig. I was very skeptical at first, but now I'm obviously quite a believer, and I came on board as president of the company, and we hope to we hope to make this really happen. Anyway, let's talk a little bit about energy storage and what's happening. I mean, the energy storage is something, like we said, that we've talked about a long time, and it's fundamentally because there's a lot of things going on the grid right now in terms of growth of demand, in terms of aging infrastructure, the need for growing amounts of transmission and interconnection distribution systems, which are harder and harder to build because they're located in urban areas which are crowded, and people, you have the NIMBY problem. Nobody wants things like this built in their backyard. You have this growing infrastructure on top of what's happening with renewables and wind and solar being integrated into the picture. And of course, wind is wonderful except for when the wind doesn't blow, and solar is great except for when the sun doesn't shine, and the sun isn't shining right now in where I am. So I'm sure that the PV guys are out of business for the next couple of hours. So that problem creates havoc with the grid, obviously. And the ironic thing is that for all of the gigawatts of wind and solar that are being put into the grid, and our system, and in Europe, of course, even more, basically it's not reducing the demand for thermal plants, because all of the We need to have as much generation capacity available for when these intermittent renewables are not generating electricity. And so this, ironic effort to, or this effort to bring renewables into our grid is having, the impact of actually increasing the amount of thermal power plants that we need in order to compensate for when that generation capacity is not available. This is all as much as to say that the broader problem is simply the decoupling of supply and demand. In other words, having storage in the supply chain someplace. It's often said that that the electricity grid is the largest machine that mankind ever built, and I think that's a true statement. I wouldn't want to have to figure that out in practice, but that's probably true. In reality, it's something like globally a $2 trillion supply chain, and this supply chain has virtually no storage. The only storage, and we'll get onto this later, the only storage in the electricity grid today is pumped hydro for all intents and purposes, but it's an asterisk, it's a detail in comparison to the actual size of the business. But there's no other supply chain on the planet, and I'd love to hear from anybody in the audience if they can think of one. There's no other supply chain on the planet that doesn't have storage in order to optimize its efficiency. I don't care what it is. It could be coal or gas or oil. It could be textiles. It could be metals. Even sushi. Sushi has the same properties as electricity. You want to consume it pretty much the moment that it's produced. And even sushi has a supply chain with storage involved. If it didn't, imagine how hard it would be to get proper Japanese food if every time we wanted to order a sushi, we had to have a fisherman standing right there, jump out into his boat and grab a tuna for us so that we could have, some Maguro sushi. It would collapse, and it wouldn't function. And yet that's how we run our electricity grid, such that, one of the stats on this slide is that 25%, the Department of Energy estimates that 25% of all the distribution assets, hundreds of billions of dollars worth of distribution assets in the United States, and worldwide, by the way, I think the statistic would apply equally elsewhere, and 10% of all generation and transmission assets are used less than 400 hours a year out of 8,760 hours in a year, which, basically the entire grid, this colossal machine, this large machine, the largest machine that mankind has ever built, is built to produce the last kilowatt hour at the peak hour of the peak day of the peak year. And the rest of the time, a lot of this infrastructure is sitting idle. And the reason why that's happening is that there's no electricity storage in the system. If there were, we could level that out and handle that much, much more efficiently. Now, it's not that there's no electricity storage because there's some sort of an oversight that somebody forgot to build it, or that the people designing the electricity supply chain aren't as smart as the people who are designing all other supply chains. On the contrary. But the problem is that storage of electricity is simply too expensive. And it's cheaper to throw away, effectively, to not utilize capacity at night or off-peak and produce more electricity than it is to store the off-peak electricity and redeliver it to ourselves on peak. That's the fundamental problem. And that's, if you will, the problem and the challenge that we are addressing or attempting to address with our business strategy. Now, electricity, you can move on a little bit if you want, Craig. Sorry for that long introduction. But the electricity storage can provide all sorts of things. It improves the efficiency and profitability of the existing assets. You've got the ability to not engage in this tremendous infrastructure investment because you can put electricity storage all throughout the supply chain, which is sort of primitively illustrated on the top of this slide. But at the point of generation, before transmission, before the actual distribution system, and throughout the substations and in the load centers. And so you can take the pressure off of the system and not engage in complex and extremely expensive upgrades for small increments of power consumption.
But Steve, let me just interrupt for a second.
Sure, please interrupt regularly and stop me.
Well, I find this slide here very telling insofar as that, yes, it speaks to the fact that this is the world's largest supply chain with no storage, but it also the answer is kind of implied in the slide here, and that is, and the answer as to why don't we have this, and it seems to be because you've got assets all over the place, from generation to transmission and distribution, to ultimately to load. So the question is, if you're going to have this stuff, I don't think anybody doubts that storage is good, and especially if you can do it cost effectively. This is the reason we're trying to do all this stuff with pumped hydro and even more exotic stuff with compressed air and so forth. But the question is, who owns the asset? In other words, if I can say, well, this is purely a T&D, a transmission and distribution asset, which I wouldn't, or I couldn't, but if I would, in other words, if I could say, well, who benefits from this thing, and therefore who should pay for it? I think this would be a much easier question to answer. But the problem, it seems, and it's, as I say, it's implied in this slide here, is that there is no natural home for this. It's unclear. Everybody's going to benefit from this thing, so why shouldn't everybody pay for it? Why should one asset-based category pay for it?
Well, Craig, great question. But the answer isn't that there's no one that there's no one right place for it. The answer is that there's multiple right places for it, and there are ways of monetizing those benefits at each point in that supply chain. Why don't you kick forward to the next slide, and it talks a little bit to this point, and then I'll expand in order to answer your question. This basically divides the problem into end user benefits, which is sort of the green, in other words, the load center, and then the grid and utility benefits, because the grid finally divides itself into the stuff that's the responsibility of the utilities, in other words, before the meter, and then the stuff that's the responsibility of the landlord or the property owner, which is behind the meter, right? So, starting with the easy one, behind the meter. Okay. Behind the meter, you've got people investing a lot of money today in UPS systems and power in generators and diesel, to provide backup power in the case of outages and so forth. So people already are familiar with the problems of reliability and also, of course, power quality. So you've got especially data centers and so forth. But what energy storage, what inexpensive energy storage, and this is the difference, there's a big difference between energy storage and power storage, okay? Energy storage allows you to serve your needs over a long period of time. Power storage allows you to basically smooth out things like, fluctuations in frequency or voltage, or it allows you to, jump in, for a short period of time with a lead-acid UPS system to, give you 15 minutes or something like that to whatever it is, shut down your systems or get out of the building or, handle a very short interruption. But energy storage allows you to do all of that and a whole lot more, and that's where these other things come in. In other words, if you actually have hours and hours of energy storage in a load center, you can, instead of paying the utilities or the providers high prices for peak power, you can buy your power off peak. You can buy really cheap power and deliver it to yourself when you need it during peak hours. You can also radically mitigate your demand charges. And that's a big. I know that's. I don't know about you, but that's about half of my electricity bill is just the demand charges. If you're able to avoid using power from the utility during peak hours, and in other words, charging your battery off-peak when there aren't demand charges, and then redelivering that power to yourself and not using power from the grid during the peak hours, you're able to radically reduce your demand charges. And then you can even participate, if you've got enough energy storage, you can even participate in demand response programs or in frequency regulation. In most ISOs, demand response is actually an acceptable form of frequency regulation, so you can actually even bid into the ancillary services market if your battery's large enough. And so you've got multiple benefits, monetizable benefits, Craig. The actual energy arbitrage, buying cheap energy instead of paying for expensive energy, reducing your demand charges, that's real money, real cost savings, and then replacing your UPS and backup systems and ancillary services, all of that combined gives very compelling economics. In fact, we've looked at this in many major cities in the United States, and the cash-on-cash returns for our systems for the end user, for the load centers, are something on the order of 25 to 30% per year. Okay, pretty compelling. not to mention the externalities. I mean, not to mention that this provides, shall we say, a Walmart or a Costco or any other retailer that's trying to cast themselves in the green energy space as actually running themselves entirely off of renewable energy. If you can store energy, you can deal with the intermittency. You can buy off-peak nighttime wind power, which is available for practically nothing, and run your entire business off of that and genuinely be green, not just by buying somebody's green credits and pretending that you're using renewable energy, but actually using renewable energy. So there's huge benefits, monetizable real dollar benefits on the end user side. On the grid side, that's the easy part. The grid side, you've got many different points. You've got the point of generation, you've got transmission, you've got distribution, and at each of these areas, you've got a lot of monetizable benefits. They're largely similar, meaning you can go off peak to peak. You can get capacity payments if you've got a large energy storage system on the grid. You can engage in ancillary services. And these are this is real money that you can earn, even as an IPP. In other words, you could build a battery farm, a 50 megawatt, for example, battery farm, put it on the grid, and run it independently as an independent power producer and make good money. The same type of high returns that we were just talking about. 20+% cash on cash returns, which leveraged in the way that utilities are able to leverage, obviously is extremely meaningful.
Yes.
I know you're pushing me to the other slides to get me to move on. I appreciate
that.
Well,
I do want to do this. I do want to get to, this is a very interesting discussion of all of these areas. So first of all, huge global market. Nobody disputes that.
Well, that's the thing. Actually, I dispute it. I mean, like the big question, of course, in the energy storage business is it a $400 billion market or a $600 billion market? I mean, that's kind of a silly debate. The truth is, and this is the sad truth, the entire energy storage business in 2010, grid-level energy storage, was $1.5 billion. That seems pretty anemic for a $500 billion market, wouldn't you say, Craig?
Yeah, I would, but of course the slide I'm putting up here kind of speaks to that. In other words, there are...
Why? Exactly. It's because there isn't a product. There's huge demand. Not nobody. I mean, every major analyst talks about this trillion-dollar market. Michael, my colleague, and I often refer to the energy storage business as the $0 trillion market. In other words, it has tremendous potential, but today it's basically nothing. And the reason is exactly the slide that you're pointing to. This slide is maybe a little complicated to read, but this is a great curve that EPRI, which is the Electric Power Research Institute, which is the consortium of utilities, the research and investigation arm, which is a nonprofit group created by all the utilities in the United States. They've done a lot of research on energy storage, and they've come up with what this is basically an elasticity curve. In other words, it shows all the different potential uses of energy storage and what the value of the benefits of energy storage, and it sort of ranks them by highest value toward the y-axis and then goes on to the right to the lower values. And you can see this is basically a classic elasticity curve, which talks about up to 50 plus gigawatts of demand in the United States alone. To put that into perspective, that translates into about 250 gigawatts of worldwide demand. But you can see at where we are today, which is the gray arrow, which is north of or around $1,000 a kilowatt hour for providing energy storage. There's not a whole lot that you can do with it that makes economic sense. And that's why you're seeing a very anemic market, and that's why most of the projects that you're seeing are, experimental, touchy-feely kind of projects among various utilities, trying to experiment, see what they can do with it, see if they can make money off of this. And most of the big benefits is this sort of transmission and distribution deferral, which the utilities can benefit from and monetize on their own books in some sense. But even that is difficult because energy storage hasn't yet, in most public utility commissions and ISOs and so forth, that hasn't been incorporated in the rate basing methodology that utilities are able to incorporate in their capital program. So very, very anemic. So if you go to the next slide, the bottom, anybody can see what happens when you get down to our cost point. We can produce zinc air energy storage at about $160 a kilowatt hour. That's groundbreaking in terms of, if you look at the actual demand and the monetizable benefits. You've got to, the market suddenly goes from a couple of gigawatts, really worldwide or even around the nation, to dozens and dozens and dozens in the United States alone, to really start to address all of those aspects of the supply chain that we're talking about, from generation all the way through load centers. And that's really the bottom line of what we've been trying to do, is challenge the incumbent technology. In other words, provide energy storage that can actually compete with the way that these problems are all being solved today. These problems aren't being ignored; they're being solved, but they're being solved with marginal generation capacity. As soon as energy storage becomes cheaper than marginal generation capacity, everybody's got a strong incentive to deploy it. So,
yes, I'm with you. Question from the audience: is this delivered energy TCO, total cost of ownership, I presume, or storage cost only?
This is the cost. The $1,000 a kilowatt is, and for 6 hours, which is $160 a kilowatt hour, is the cost of our DC to DC system. So in addition to the cost of the battery, you'd have basically the power electronics to incorporate it into whatever you were trying to use it for. So we don't supply that. We work with ABB or GE and Siemens, the major inverter suppliers and so forth, and because everybody's got their own deployment and everybody's got their own implementation, which requires different power electronics. And then, so your total cost of ownership, capital cost of ownership, and we'll get to levelized cost of energy here in a minute. Total capital cost of ownership could range from that $1,000 a kilowatt up to $2,000 if it were an urban deployment in the middle of New York City, for example, or to something like call it $1,200 or $1,300 if it were more of a classical deployment around a substation or transmission line.
Right. So, and as we're going to get to, this has implications not only in utility scale energy storage, but in electric transportation. And just coincidentally, I think it was just today, there's the Department of Energy, Stephen Chu, made another public announcement about how the support for driving down the cost of what I guess is presumably lithium ion. But in other words, in terms of electric transportation, we're trying hard to get to $300 a kilowatt hour.
Well, you're jumping ahead a couple slides, but absolutely. Secretary Chu's been a tremendous advocate of this, and in fact, there's a quote on one of the slides toward the end of Secretary Chu's. Basically, he himself has said that, in his opinion, metal air batteries are the answer. And we'll come to why metal air batteries are the answer. There's a lot of really obvious reasons why metal air batteries are the answer. So should I save that when we've got the slides, or you want me to go to that?
I suppose so. John Robbins asks, are we talking about kilowatts or kilowatt hours? In other words, power, energy?
Our product, our first product, is a grid scale product, which is, go to the next slide, if you would, yeah? This is the Aurora 1000, 6000. 1000 refers to the power, and 6000 refers to the energy. So it's a 1,000 kilowatts or a megawatt battery with 6 megawatt hours of storage. So it's basically a 6-hour battery. Okay, this megawatt battery would be in a standard ISO shipping container. And then you would deploy it. You could literally park it behind a building. You could put it near a substation. You can stack them like you can other shipping containers. So a very convenient form of delivery. And of course, they can be transported directly in trucks or rail cars. So we're talking about $1,000 a kilowatt. So because there's 6 hours, so it's $160 a kilowatt hour. All right. The other key feature of the product is that we believe that we can cycle this up to about 10,000 true cycles. By true cycles, we mean when lithium-ion batteries talk about cycles, they talk about reverse changes of direction. When we talk about cycles, we mean you charge at night, you discharge during the day, and during that 24-hour period, you might be doing ancillary services and changing direction multiple times. But we consider that daily cycle to be one cycle. So we believe that our product will last up to about 30 calendar years, right? And the reason, obviously, is that we're developing a utility quality product, and that's the type of time frame that utilities think in. So that gives you a sense of what the product is and how we plan on addressing that market. All right. Competition. I mean, there are other battery producers out there. We don't look at other battery producers as our competition because batteries today do not supply the services that we're aiming to provide. Batteries don't provide peak power on the grid. They just don't. The thing that provides peak power on the grid is peaking plants, and that's our competition. Obviously, other ways of solving that problem, like new transmission and distribution spending, which tends to be even more expensive, or demand response and so forth. These are the true forms of competition. So the next slide is really telling, because this is really where the rubber hits the road. This is a complicated slide. Let me try to explain it. Basically, the line on the right, is the black line, speaks to the levelized cost of producing a marginal kilowatt hour during peak demand by a peaking plant, because that's what happens. In other words, in real life, gas turbines provide the peak energy that we're using on the grid. And the cost of doing that runs from about 22, 23 cents a kilowatt hour up to almost 30 cents a kilowatt hour. That seems really expensive. Nobody's paying that much money, but that's how much it actually costs for that peak kilowatt hour that's produced. All right?
Depending on the price of the feedstock, in that case, natural gas.
Right. On the right-hand side, on the right-hand y-axis, you've got the feedstock price, which goes from, I've taken it from $3 up to $8 just to give a range, but that gives you a sense of what that cost is per kilowatt hour for a peaking plant. Okay? Mm-hmm. Now, any technology that's to the right of that line is not interesting, in my opinion, because if it's cheaper for a utility to produce energy using a peaking plant, that's what they'll do. That's what public utility commissions do, is they force utilities to use the cheapest technology to solve the problem, and that's what peaking plants do. Now look at our line. Our line is the orange line in the center. Our line talks about, again, this is the levelized cost of a kilowatt hour of peak energy, taking into consideration everything: the capital cost, the cost of installation, the amortization of that capital cost. The input, in our case, is off-peak electricity, and you can see that I've run that from up to 6 cents in terms of the cost of off-peak electricity on the left-hand side. It includes the round-trip efficiency, all of the factors that go into calculating what a kilowatt hour costs. And you can see there's no overlap between those two lines. Even if off-peak energy costs 6 cents and gas costs 3 cents, our solution is still cheaper. And that's the bottom line. In other words, if you can provide a solution that does this, then that is a game. To quote you, Craig, if you don't mind, in our view, that's a game-changing technology.
I completely understand. And this next slide just speaks to something that you covered earlier, and that is the
pumped hydro. Right now, the only form of energy storage that we've got on the grid really is pumped hydro. You can see that this almost looks like those things of the solar system that you sometimes see to compare the size of the sun to Earth and Pluto or whatever. And the reality is that over 99% of all energy storage in the world is pumped hydro today, 127 gigawatts. Now, 127 gigawatts seems like a lot, but it's a tiny amount compared to the size of the global electricity grid. This really talks about, this speaks to the different attributes of the system, and it's worth stopping here for a second just to say that the other thing that we're extremely focused on are two other major features. We often talk about, I'll back up, we talk about the four key factors of the sort of like game-changing technology. First is cost. We've covered that a lot. Second is energy density. The solution must have very high energy density, because the best way of solving the energy storage problem is to have distributed energy storage. In other words, to put energy storage in the load centers themselves. That debottlenecks the transmission and distribution system as well. And so, but in order to fit it in the load centers, you're talking about putting energy storage in, for example, commercial buildings in New York City where space is extremely expensive. You can't take up half of a building with an energy storage solution. It has to be extremely compact. And the third thing is safety, of course, because once you start talking about putting energy storage near load centers, residential buildings, commercial buildings, shopping centers, whatever it might be, obviously, you're not going to win too many friends if you burn some of these things down. So the safety is a crucial factor. And,
well, it's funny you mentioned this because a listener wrote in a question about energy density, I presume more related to electric transportation, where obviously it's a critical
yeah, we're going to
issue.
get to that. We're going to get to that. The simple answer is that if you look at our system on apples to apples, like versus A123's lithium-ion batteries for grid storage, the system level, and that's the only thing that counts. It doesn't matter what's happening at the cell. It matters what's happening at a system level because you've got all the overhead involved. System level energy density is about 14 times the energy density of lithium-ion, the zinc air solution. So it's a step change. Okay.
Mm-hmm.
So the energy density is important. The safety extremely important. Zinc and air. I needn't tell you. Zinc is a dietary supplement, Craig. Air is air, generally very harmless. And even the electrolyte that we're using is similar to the chemistry used in toothpaste. Okay,
Mm-hmm.
So you're talking about a fundamentally exceptionally safe technology that even doesn't have the chance, even when it overheats, is self-correcting. So unlike lithium-ion, you've got an incredibly safe technology. This sort of speaks, there's our toothpaste, right? So why does zinc air solve these problems? So why is zinc air technology so valuable in this context? Oh, you jumped forward a slide. Okay.
I wanted to do this simply because you're talking about zinc air generally. Why don't I?
Okay,
I want to jump forward and then jump back if I could.
No problem at all. Go to the next slide. The next slide shows a comparison by looking at button cells. Okay.
Are you talking about the
next slide after this one in sequence? If we're talking about zinc air technology, okay, there you go.
Walk us through this and recognize that we're not generally battery
right, not battery specialists. So without reading the stuff, you can see if you look at the left and the right. Okay, the left is a typical button cell. We don't make button cells, but this is just by way of illustration. Okay, a typical button cell will have on the top. You're looking at the anode. On the bottom, you're looking at the cathode. The cathode is basically the reactant that's used to extract the energy from the anode. And in a typical battery, about 50 to as much as 70% of the weight and volume and cost of the battery will be the cathode. Okay. And so this is this looks at that's a standard sort of zinc anode cell where you've got a cathode reactant. A zinc air battery, like on the right. Basically, what you're doing is you're taking up the whole volume of the battery with the energy-producing agent, which is the zinc. And all that you've got there is that thin black thing on the bottom is the air cathode, which allows air to come into the system. If you go to the next slide, it'll become a little bit even more obvious. Think of a gasoline engine. A gasoline engine basically is a gasoline-air battery in some sense, where for every tank of gasoline that we consume in our car, we consume about a ton of oxygen to combust that gasoline. Okay? If we had to carry that oxygen around with us, we'd be carrying a trailer of reactant around to burn that gasoline effectively. And that's what other batteries do. That's what lead-acid batteries do. That's what lithium-ion batteries do. That's what all, other than metal air batteries, that's what all batteries do, is they're carrying that expensive and heavy and volume-consuming overhead in the cathode around with them. A metal air battery resolves that problem because we're using ambient air. The difference, by the way, there's a big difference between gasoline and zinc, where gasoline, of course, converts that air then into pollution, into CO2 and all sorts of other emissions, whereas a zinc air battery breathes. It breathes in oxygen and it breathes out oxygen. In other words, when it's recharging, you're just discharging the oxygen. So there's absolutely no emissions whatsoever.
Okay, good.
And sorry?
I was just going to suggest that we go back to this analysis, this kind of financial analysis.
Sure. Go. Jump back to the slide after the one with the attributes of the system. I mean, the bottom line is we talk about 4 different attributes: cost, energy density. This speaks to cost. But go to the next slide. these are the various difference in capital costs between EOS's battery and all other solutions. But this one actually takes it back to levelized cost of energy again. But anyway, I was saying cost, energy density, safety, and cost. Let's not forget about cost. That's what we're going to talk about, the four different issues. So if you look at this again addresses the levelized cost of a kilowatt hour for shifting energy from off-peak to peak, okay, which is that's the big problem, if you will. That's the the elephant in the room. And the cheapest thing out there, other than the gas turbines, we'll come back to gas turbines in a second. The cheapest thing out there is pumped hydro. You build pumped hydro wherever you can. The problem is you can't build it in too many places. You need very special geological conditions in order to build it. It needs to be built in very large scale. And by definition, it's being built away from the load centers, which is where you really need it. But cost-wise, it delivers a good product. The dotted line really is that line that you've got to beat. In other words, you've got to get underneath that line to provide peak energy cheaper than what a peaking plant can achieve. And then the bottom, over on the gas turbine side, the bottom of the gas turbine cost range is really combined cycle plants. But those aren't used for peak energy. Those are used for baseload. And so not really, that's sort of apples and oranges a little bit. But the apples to apples comparison is the dotted line that goes across. And you can see our technology is cheaper than gas turbines for peaking. It's almost as cheap as combined cycle plants, and it's cheaper than pumped hydro, which is if you will, the only other real incumbent energy storage technology. So, should we move on?
Mm-hmm.
Unless you got any questions on this.
No, that's completely fine. Go ahead, please.
So let's get back to EVs, which you talked about before. We don't need to talk about why we need EVs. I don't think everybody understands it. We're talking about, oil, energy security, climate change, the wars that we have to fight in order to get access to gasoline. The reasons, the number of reasons to convert to an electrically based transportation grid are very compelling. So EVs, interestingly, have the same challenges that grid storage does, because ultimately it's about cost. Today, today it would cost to get a battery for an electric vehicle, a lithium-ion battery for an electric vehicle that would reproduce the range of an ICE vehicle, a gasoline-powered vehicle. You would need about 100 kilowatt hours of energy in order to reproduce that range. 100 kilowatt hour battery for an electric vehicle using lithium-ion would cost about $75,000, and it wouldn't fit in your car. So if you're back to that trailer thing, you'd have a trailer of batteries that you'd be carrying around with you. So, obviously it's $70,000 for a battery. You're not at a mass market device. And ultimately, Joe Sixpack is going to buy his electric vehicle when it's cheaper to own an electric vehicle than a Toyota Corolla. And until that day comes, electric vehicles are going to be for early adopters and very specialized segment. And so ultimately, we've got to get to a price point that makes sense.
Yeah, there's no question about it that the consumer has a vote in all this, in this migration to electric.
Yeah, obviously, the biggest vote.
And interestingly, I think there are probably 5 or 10% who are going to buy these things anyway, even if they are more expensive, and there are another 5 or 10 who aren't going to buy them regardless. But that leaves 80% of people looking at this thing. I'm watching this very closely, and I certainly believe that over the next 5 or 10 years, you're going to have a lot of pragmatists saying, what does this really mean to me? And obviously, something that we're talking about here affects this calculus very sharply. Let me throw in a couple audience questions here, and these are, of course, not. These are kind of scattered around in your presentation, some of which I happen to know you have slides that you're coming to, but I might as well just insert them here. Can the battery go to 100% discharge?
Yes, we've designed the battery for 100%, to go from 100% charge to 100% discharge. Yes.
Okay. What is the actual number for energy density in terms of kilograms? Watt
hours per kilogram?
Yeah.
In our grid in our grid product, let me so I don't make a mistake. Let me pull up those numbers. But in our grid product, it's over 100 watt hours per kilogram. But bear in mind that we're not really in our grid product. We're not really trying to economize either space or weight, because we don't care as much as we do for an EV product. I'm just going to pull up the to give a correct answer to the question. A different presentation. The energy density for our automotive product, we think we can get up to higher on a gravimetric energy density basis, which is well above 100 watt hours per kilogram, but more relevantly almost, our volumetric energy density can be as high as nearly 400 watt hours per liter, and that's the key sort of like factor, because if you do the math on that, if you've got 300 liters in of void space, even in a small car for a battery, that gets you above the 100 kilowatt hours that you need in order to reproduce the range of an ICE vehicle.
Yes, and that is a critical issue with respect to electric transportation, no question. Here's another question. I'm glad this was asked because I meant to mention it and I forgot. When the first time I mentioned zinc air to somebody, actually a pretty senior scientist, he goes, "Oh, well, those things aren't rechargeable." And I go, "Well, this is I don't know what the secret sauce is, but this is absolutely rechargeable." Can you speak to that, please?
Yeah, sure. That's always been the challenge. Look, zinc air batteries have been around for decades. They're used broadly in hearing aid batteries. They're considered to be obviously very energy dense. They're very small. They contain a lot of energy. They'll last a long time. They're incredibly cheap and so forth. There's just one problem, that nobody's been able to make them rechargeable, and not for lack of effort, by the way. The Japanese started trying to make rechargeable zinc air batteries back in the 70s, and there are a lot of problems which have obviated that, which have made that impossible. Zinc forms dendrites and these sort of like spiky, non-useful, non-conductive formations on the anode. And they pierce the membrane in the battery, which is a classic point of failure and point of fragility, and also very expensive. More importantly, you have CO2 evolution in the electrolyte on recharging, which clogs the air cathode and makes it not rechargeable. And you've got, in short, severe problems. I can't really go into the proprietary nature of what we've done, but I can tell you generally what we've done. Okay, which is, instead of all of the efforts since the 1970s to make zinc air rechargeable have been efforts to mitigate the effects of these problems. In other words, to do CO2 scrubbing, or to somehow mechanically replace the zinc anode so that, once dendrites formed, and to somehow repair membranes. I mean, and so very expensive, kludgy, ham-fisted ways of solving the problem. What Steve, the inventor, did, he basically went back to first principles and redid the chemistry. In other words, he started over again. The only thing that our battery has in common with classical zinc air batteries is the zinc and the air. Everything else about our battery is different. We don't even use a membrane. It's completely, it's removed from the system. There's no separator. There's no membrane. We've changed the electrolyte, we've changed the electrodes, we've changed the current collectors, we've changed everything about the battery in order to not mitigate the effect of these traditional problems, but to eliminate them completely. Our battery doesn't form CO2. Our battery does not have gas evolution. Our battery does not have dendrites at all. Our battery does not have a membrane at all. So we've literally removed the cause of the problems rather than trying to solve the problems.
Okay, that's good. And there are a couple of questions having to do with the business numbers here, but I happen to know that you're coming to that. In other words, what's the trajectory for mass production, et cetera. So why don't I just hold off on that, let the listeners know that you're coming to that shortly. And let's just carry on.
Well, we can scoot through. There we go. I mean, this slide is just interesting from a nationalistic perspective. The United States consumes about 19 million barrels of oil a day. Okay, but we produce 9 million barrels a day. We actually are one of the largest. Most people forget the United States is the third largest oil producer in the world. But we consume 19. We have a deficit of nearly 11 million barrels. But the interesting thing is that 11 million barrels of, a deficit of nearly 10 million barrels. The 11 million barrels of that 19 that we consume is for vehicular transportation. So we can dream of a world where if we could replace the gasoline that's used for vehicular transportation, the gasoline and diesel, you could dream of a world where the United States doesn't import oil. In fact, we could be an oil exporter. I mean, as crazy as that may seem, but it's not impossible. So let's just move on. That's just an interesting side point.
Well, you bring up a good point, and that gets into the numerous reasons to get rid of our addiction to oil. And certainly the fact that we're borrowing $1 billion a day and sending it to people who are essentially enemies of what we stand for is a good one. It's a heck of a good one. But
it's an awfully compelling reason. If I were designing energy policy, that would be something up on my radar screen.
Yeah, I should say. So go on, please.
Anyway, look, the market is very huge. I mean, this next slide really speaks to that. We know how big the electric vehicle marketplace is, but what we don't know is how big the market would be if electric vehicles really did cost the same as gasoline-powered vehicles. I think that would be really interesting. I mean, I think, I know a bunch of, you ask all your friends, Craig, and one or two of your friends probably owns an electric vehicle, but most of them don't. But most of the people that you ask will say, yeah, my next vehicle, I'll probably be getting a hybrid or an electric vehicle. People already have that in their consciousness. But if you were to say to somebody, look, instead of this Toyota Corolla, I can give you an electric vehicle that's the same cost as the Toyota Corolla. It's got the same range as the Toyota Corolla. The only difference is that instead of 20 cents a mile for gasoline, you can pay 2 cents a mile for electricity. Would you buy that? I'd buy that vehicle. Anybody would buy that vehicle. And so I think that we might be on the cusp. I think you said this in our conversation when we were in New York. We might be on the cusp of something explosive with respect to electric vehicles if we can produce the product that the consumer needs.
Yes, and we're going to get there. There's no question about that. And this obviously, I think, is a gating factor. In other words, your ability to deliver product as early as 2013 that speaks to this is a huge factor in moving this thing forward. The only thing you're missing, I know you're doing this deliberately, but the only thing that you're not talking about is rapid charging. In other words, the fact that that is not, until we have ubiquitous fast charging or battery swapping, which we're not going there, but we probably will get to ubiquitous fast charging. And until we do, there is going to be a difference in the mentality of an EV driver versus an internal combustion engine.
Well, you're handing me softballs, Craig. You gotta throw some harder stuff at me. But we'll skip forward 2 slides or go. The next slide is quick, and then really the bottom line is what are the barriers? One is the high cost. We've talked about that. The range. Everybody knows about range anxiety. Charging up. Who wants to sit around for hours waiting for their car to charge when I can put gasoline in my car? It takes me 3 minutes. And then safety. Safety is sort of like the unspoken one, the sort of like lurking in the closet here. The bottom line is that current EV batteries are unstable and they catch on fire, and that's a real problem. If it isn't a problem for consumers today, it will be tomorrow. So if you skip forward though, in the next slide, what we're able to do with the Zinc Air technology is we're able to create a 100 kilowatt hour battery, okay, that can get you normal, like 175 peak horsepower, 340 mile actual driving range, 2 cents a mile cost for energy. Great product. But you're right, the one minor little fly in the ointment is, well, it takes a long time to recharge, and that's true. But the interesting thing about our technology, and this is not first generation, it's second generation, but the interesting, and that we actually have a product built around this called the Vista, which is our next generation battery. The interesting thing about Zinc Air batteries, what's happening very quickly in the chemistry is that when you're discharging the battery, the zinc is basically dissolving into the electrolyte. And so what you've got when the battery is fully discharged is you've got this liquid with all the zinc in it. Well, what you're able to do actually is just drain that electrolyte out of the battery. Just pour it out. And pour in new electrolyte that has zinc metal suspended plus your normal charged electrolyte, and you could keep driving. So we could actually produce a product. The Vista product, the way this is, what that's designed for is instead of going and putting gasoline in your car, what you would do is you would go to a charging station. Instead of charging the battery, you'd simply drain the electrolyte out and pour new electrolyte in. It would take 3 minutes, just like, and by the way, you'd save the old stuff that you drained out, because at the charging station they could recharge that cheaply at night and sell it to the next guy who came in the next day. So it's totally reusable. But for you, when you're driving to grandma's 1,000 kilometers away and you need to just refuel, you could actually do that with this almost exactly the same experience that you have today putting gasoline in your car. Only difference is you'd just be draining the other stuff out and saving it at the station. That obviously requires massive change of infrastructure, but you can absolutely do that with the technology that we're producing, which is really, really interesting. Now, I would note that battery is still electrically rechargeable. So 99% of the time when you weren't driving 1,000 kilometers that day, you'd be charging up at night in your garage just as you normally would. It's the one time when you needed to drive a long distance, you'd have the ability to actually refresh the battery or refuel the battery in addition to having the ability to recharge it. And there's Steve Chu at the bottom of the slide. I mean, he's got a lot of great quotes. So.
Yes, and yes, he's been in the news more recently than this as well. So I'm not a battery chemist. I find, I don't know. I'm going to. I know people are going to want to challenge you on that, according to the first law of thermodynamics. In other words, the conservation of energy. In other words, you're pouring something into your. You need to pour energy into your gas tank.
Right. What we're doing is we're pouring a mixture of electrolyte and zinc metal that's actually suspended. You can do this. It's well-known technology in the metallurgy industry. You suspend the zinc metal in the solution, so it pours, okay? And together with the electrolyte, that mixture goes into the battery, and then using an electrical reaction, we then we bring the zinc onto the anode plate, okay? And then from there, you carry on just like the battery had been charged.
Oh, interesting. All right. Well, very good. On we go.
So anyway, now we're talking about cost comparisons. Obviously, if you get down to the $100 to $200 a kilowatt hour range for EVs, you can see what the payback is versus ICE vehicles. It's less than a year. It's a very compelling value proposition for any consumer. I mean, that becomes, I think, the ultimate transportation no-brainer. So that's kind of what we're shooting for. If you go to the next slide, you can see that you can line that up. You've got your Toyota Corolla on the one side. You've got your Leaf with its various attributes and its charging, its range, and so forth. Your first generation EOS EV, which has a 340-mile range. 2 cents a mile cost and the right sort of power, and then your next generation, which allows you to actually recharge instead of 6 hours, you've got 3 minutes to be able to recharge. And 6 hours is obviously the standard charge, not a rapid charge. But so that's really where the rubber meets the road, I guess you could say.
Right. Very good. A couple more questions from the audience.
Sure.
Yes, well, certainly the flow battery, this has to do with the flow battery defeats the need for better place schemes, which is absolutely correct. I've always, I'm a big fan of Better Place and, Shai Agassi as a presenter and as a businessman. And I think that I think that this has legs in places like Israel where, you have a small landmass and you've got, enemies all around you from whom you desperately don't want to be buying oil. In the United States, it strikes me as a non-starter, though he's doing a very good job at presenting his case all over.
We didn't come today to talk about the merits of battery changing. I think battery changing kind of misses the point. The reason why anybody's even talking about battery changing is that batteries today don't solve the problem. So yes. My view is, create a battery that solves the problem. Forget about battery changing. Create a battery that solves the problem.
Right, exactly. And here's a question. Nissan Leaf electricity costs are approximately 4 to 5 cents a mile. How does this estimate? Where did you come up with 2 cents?
Well, 3 cents is what's on the Leaf estimate, and I took that from their website. So if somebody's got a better number, then I'm happy to change it. But so I assume that they produce that number, based on round trip efficiency and depending on what the underlying energy cost is. It's not really the point, whether it's 2 cents or 4 cents or 3 cents. It's kind of like that's going to depend on where you are, and if you're doing a fast charge, obviously it's a whole lot less efficient, so you're going to be paying a whole lot more and that type of thing. The point isn't 2 cents or 3 cents versus 4 cents. The point is 2 cents versus 20 cents. That's the point.
I'm with you. Okay. Let me see. Here's a summary. I know we want to talk to, let me just make sure that this speaks to, yes, good. I would like to, I know a number of people have asked about, well, where are you as a business? And I would certainly just ask you to present this slide and speak to that, please.
Sure. Where we are, we've basically proven out this technology. We're now scaling up the technology. Our full-size, we've proven out the technology using full-size cells. Our full-size cells are about 3 by 6 inches. And then basically you accumulate them in stacks and then modules and so forth. And in a megawatt-sized battery, there's 200,000 of our cells that are all sort of like firmly linked together in series and in parallel to produce the product. We are now scaling up. In other words, our full-size stack, what we're calling it, is a 17 kilowatt, 100 kilowatt hour stack, which is about the size of a bookshelf. And we are now building out those stacks. We should have prototypes, or we expect to have prototypes of those stacks operating first quarter of next year. And we expect to line them up into a megawatt-sized prototype by the end of next year, and expect to begin producing what we're calling the Aurora 1000, 6000, that battery we talked about before, the 1 megawatt container-sized battery for the utility industry, beginning in 2013. You're probably wondering about the EV battery, and the EV battery, of course, is the big sexy one. The reality is that we won't be producing the EV batteries. The design and manufacturing challenges for EV batteries are extremely daunting and really not our core competence. So what we're doing right now is we're working with some potential partners and hope to create a licensing partnership with one of the major Tier 1 suppliers or OEMs to build out the battery for the EV, for the automotive applications. Now, naturally, that's going to take a lot longer. And certainly the semi-flow battery or the Vista battery is many years away. But I would expect, even with the best of efforts and the best of intentions, your Aurora battery, your initial Aurora automotive battery wouldn't be available probably until 2015, and that's if we started working on it with somebody tomorrow.
Okay. Well, interesting stuff. Do these? There's a question from the audience. Do these batteries require a specialized battery management system?
Yeah, all batteries require a battery management system of some sort. The overhead on our batteries is extremely light. Basically, there's no moving parts to the battery. All you have is basically a pump that's pumping the electrolyte, circulating the electrolyte through the system. So you need to monitor the electrolyte and the pH and so forth, but we don't even bother monitoring individual cells the way that a lithium-ion battery management system is forced to do. So our battery management overhead is extremely light.
Yes, well, I think that was the nature of the question. In other words, compared to the BMS in a lithium-ion battery
is half the battery. Yeah.
Yeah, exactly, and it's hugely important. If at the cell level, if they're overcharged by a fraction of a volt, you get a mess.
Yeah, you get chemical runaway, which leads to a chain reaction, which burns down your house or your car or both or whatever. Yeah, it's a big problem. Our batteries simply don't have what the military likes to call a mechanism for catastrophic failure, and so we're not forced to. And if a cell for some reason dies, it just dies and it stays there, and the battery continues to operate just minus one cell. It's not it really isn't a problem that we need to address. The battery's so cheap that you don't even bother monitoring the cells on that level. So the BMS is is basically monitoring in a megawatt battery. You've got 60 of these 17 kilowatt stacks, and each of them with an electrical home run to the control box and a home run to the electrolyte management system. And that's basically what your overhead is those 60 connections and the 60 plumbing connections. And that's what you're monitoring.
Well, that's fantastic. Steve, thanks very much. This has been a fascinating presentation. You did a great job, and I know the audience appreciated it. Anybody who missed part of it, this will be up on the website, 2greenenergy.com, in the webinars section in the next couple of days. Anybody wants to learn more about this, then certainly just shoot me an email, and I'll make sure you get hooked up with Steve. And Steve, thanks very much. Again, terrific job. Thanks for being on the show.
And thanks, Craig, for having me, and great to talk about these things. Carry on and fight the good fight and bringing all these things to people's attention.
All right, very good.
Thanks, Craig.
Until next time.
Cheers then.
Bye now.